Okay, let's take a look at Unit 7, Lesson 14, using normal distributions for experiment analysis. So we're going to determine when the results from an experiment are significant. So in 14.1, notice and wonder some distributions. What do you notice? What do you wonder? So some things that you might notice is that all of these distributions are symmetric. They also all look bell-shaped. They also all seem to have, a center at 0. They are all also the difference in means. That x-axis represents a distance in means. Some things you may wonder, what do they represent? Do they represent something real? Is it actual data, or is it something that somebody just made up? How many dots are in each of them? Some of them are easy to count, but then others, especially that last one. And what is the standard deviation for this data? You could figure that out for some of them by finding the values for each of the data points, but that would take a while. But then for others, it would be really hard to do. So those are just some things that you could notice and wonder. You might have come up with some other things. All right, so 14.2, a theoretical experiment. To see what might be happening when we regroup data, consider an experiment that takes 12 subjects and divides them into 2 groups at random. The control group contains 6 subjects and the treatment group contains 6 subjects. To explore what's possible, assume the control group results in the data 1, 3, 4, 6, 8, and 10. The treatment group results in the data 2, 5, 7, 9, 11, and 12. Find the difference in means for the original groups by subtracting the control group mean from the treatment group mean. All right, so we can bring up our calculator. And we're just going to find the means there. So 1 plus 3 plus 4 plus 6 plus 8 plus 10. And then divide that by 6. And we get 5.33. That's the mean. I'm going to slide that over. We don't need quite that much. And then I'm going to find the difference for the second group. 2 plus 5 plus 7 plus 9 plus 11 plus 12. And that's about 7.66. We're going to truncate instead of rounding. All right, and then when we subtract those, we get 2.33 is the difference between the means. All right, with a smaller data set like this, we can actually consider all of the different arrangements of the data. There are 924 distinct ways to separate the 12 values into 2 groups of 6. The frequency table shows all the possible differences in means and how often they occur. Notice that a difference in means of 4.33 occurs 7 times, and we can see that here, and so does a difference of negative 4.33. It also occurs 7 times. And so that's actually a total of 14 when you consider the positive and the negative. The dot plot shows that same information. What proportion of possible groupings have a difference at least as great as the difference in means for the original groups? All right, so we are looking at all of these values and these values because those are all 2.33 or more of a difference. All right, so we're going to count up all of those values. We don't need that anymore. All right, so we've got 1 plus 1 plus 2 plus 3 plus 5 plus 7 plus 11 plus 13 and 18, 22, 28, and 32. So we get 143, but remember, that's all the positives. We also have all the negatives, so we're going to take that number and we're going to take that number and multiply by 2. So we actually have 286, and that's out of the total of 924. So let's take that and divide it by 924, and we get about 0.31. All right, so then that's the proportion of possible groupings that have a difference at least as great as the difference in means for the original groups. So the proportion you calculate represents the probability that the original difference in means could be due to the groupings themselves. Based on the proportion you calculated for this situation, which description is most accurate? All right, so we have two descriptions. Because the proportion is so low, it is unlikely that the difference in means is due to the randomized groupings. This means that the difference in means is most likely caused by the treatment. And then because the proportion is not that low, it is still rather possible that the original difference in means is due to the random groupings. This means that there is not enough evidence to determine that the difference in means is likely caused by the treatment. And I'm going to go with B because there's still a 31% chance, which is pretty high, that the original difference is due to the way the subjects are grouped rather than the treatment. There's a 31% chance. Oh, I did not write that very well. Sorry about that. That the difference is due to the grouping. (31% is pretty high. All right, let's take a look at 14.3, simulating to decide. Researchers want to know the effect of captively raising birds on the weight of the birds. The researchers begin with 100 birds divided into two groups of 50 each. One group of 50 will be raised in captivity, and the other 50 are tagged and released into the wild. After 5 years, all birds are collected and weighed. There are more than 10 to the 29 different ways to regroup 100 birds into groups of 50 again. So looking at all the combinations would be too time-consuming to reproduce. In this case, we run simulations to determine how the original difference in means compares to those from regrouping the data. The original groups have a difference of means of 0.27 grams. Researchers run 1,000 simulations, regrouping the data into two groups at random, and record the differences in means for the groups in each simulation. The histogram shows the differences in means from the simulations. So there's your histogram. They determine that the mean difference, or the mean of the differences of means from the simulations is about 0.0021 grams, and the standard deviation for the differences of the means from the simulations is 0.112 grams. What features of the distribution in the histogram let you know that modeling with a normal distribution is reasonable? Well, it definitely looks bell-shaped, and it's symmetric. And so you can see that a normal distribution is appropriate there. Model the simulations using a normal distribution with a mean of 0.0021 and a standard deviation of 0.112. What is the area under this normal curve that is more extreme than 0.27? All right, so we're going to pull up our Desmos calculator, and we're going to use normal distribution, and our mean is 0.0021, and our standard deviation is 0.112. And we're going to find a cumulative probability, and the area under the normal curve that is more extreme than 0.27. So 0.27 is our minimum, and our maximum is infinity. And so the area under that curve is 0.0084. So it's not even 1%. It's not even a proportion of 1. That would be, or 1%, that would be under that normal curve that's greater than 0.27. All right, how can this area be used to compare the difference of means from the simulations to the difference of means from the original group? So this means that 0.84%, not 84%, 0.84% of the simulations have a difference of means greater than 0.27. That is a very low percentage. All right, so based on the area under the normal curve, is there evidence that the original difference in means is likely due to where the birds spent the 5 years? Yes, that is a very small percentage, because even if you are looking at both sides of the distribution, even if you multiplied that 0.84 by 2, now you have a 1.68% chance that the difference of means would be greater than 0.27 or less than negative 2.7. I'm sorry, 0.27. And so that is a very small percentage, and so it's unlikely that it's due to, the difference is due to the way that they were grouped. All right, and then if you want to take a look at the summary, you can take a look at that as well.